All right, so far we've figured out that our trig function was periodic with a period of 2 pi. We're only going to consider one of those periods right here, and the boundaries of those two periods are actually vertical asymptotes, which was really strange because we had a 0 over 0 indeterminate form, but it still led to a vertical asymptote after using L'Hopital's rule. Now, one of the things that I do not have to do is something like this. I don't have to do the limit as x approaches infinity of our function f of x. And the reason why I don't is because it's this same exact thing over and over again. Would it make any sense for you to do this? The limit as x approaches infinity of tangent x? No, that doesn't make any sense. So yeah, we're going to avoid doing that. We don't need to do that. Let's see, what else do we need to do? We've done domain. We've done and essentially at our domains, we have our vertical asymptotes, the numbers that we took out of it. How about some intercepts, right? Okay, so let's do that next. So intercepts, we're going to let x equal 0. In order to find our y-intercept, that should be pretty easy. So I have f of 0 is equal to the cosine of 0 over 1 plus the sine of 0. That's not as good as my last one. My last one was like perfect. All right, that one's a little bumpy, but it's not bad. So here we go. At that particular point, cosine is equal to a 1 over, and then sine of 0. Sine of 0 is 0 plus 1. Okay, this is equal to 1. So we have a y-intercept at 0, comma 1. There we go. 0, comma 1. Put a dot there. And you know what? Since it's periodic, you're going to have the exact same dot in each one of these little intervals. So there should be one here at exactly 2 pi. There should be one here at 4 pi. Should be one over here at negative 2 pi. And I think we miss the other one on the far left-hand side, which is okay. All right. All right, then. And let's see, how about an x-intercept? So we're going to let y equal 0 this time. So we have 0 is equal to cosine of something over 1 plus sine of something. So if you multiply that 1 plus sine of something over to the other side, you get just cosine x is equal to 0. So where is cosine equal to 0? It is equal to 0. Here, and just use this unit circle, this guy right up here. But also this one. So we've got a pi over 2 and a negative pi over 2, right? X is equal to pi over 2 or negative pi over 2. And since, of course, it's periodic, you can just keep on going. However, we're going to throw this guy out. Boop, boop. Why are we throwing that one out? Because you got a vertical asymptote there. It's out of your domain. All right, so we got pi over 2, which is, hey, it's right there. We got another point. Again, periodic. We've got another point. Another one. And this one would be, looks like it'd be right there. Okay, so I wonder what this graph is going to look like. Do we have enough information? Connecting the dots, we have asymptotes. Yeah, we're going to go ahead and do some calculus on it anyway. Okay, how about some symmetry? Well, I can already tell that it doesn't have y-axis symmetry or origin symmetry, even or odd, just because of the way the asymptotes are shifted around. It may be symmetric inside of each one of these little things, which, I mean, if it has translational symmetry, then yeah, that's the case. But I will just go ahead and go through the motions just because you might have to do it on another one that does turn out to be symmetric to the y-axis or to the origin. All right, so for symmetry, you still do what you do, and that is to plug in a negative x. So I'd have the cosine of negative 0, whatever, 1 plus the sine of negative x. Okay. So a polynomial is very easy to see, like you're just raising something to a power. Is it going to be a positive number or a negative number? Well, you can use the unit circle for this or the graphs for each one of these. It doesn't matter. And you should be able to get whether or not it's an even or an odd kind of thing. So let's say, for example, I chose this angle here for my x, and so then here is my negative x, right? Because negative just means it go down. For cosine, for that, that's the x value, and this is the x value. And in either one of those cases, it's the same number, right? It's the same number, which means that the cosine of negative x is just equal to the cosine of x. Well, cosine is an even function, so that should make sense, right? And then if I talk about the sine of negative x, well, here it's the y value. This is a positive number. This one is a negative number, so this is going to be the opposite of the sine. So that's 1 minus sine of x. And sine, if you think of the graph of it, it is an odd function. It's got that rotational symmetry around the origin. Now, if I compare this to my original function, it's almost the same, but it's not, because here the original one has a plus right there, plus, and our new one has a minus. And it's not the negative of the whole thing, so this doesn't have either. So no, let's say, y-axis or origin symmetry. But since it is periodic, we do know that it has translational symmetry. Okay. All right, let's see. We've done symmetry, we've done x and y axis. I guess it's time for a little bit of calculus. How do we start this calculus? We start it by taking the first derivative. Let's, just for convenience, go ahead and write the function down again. Cosine over 1 plus sine. Looks like we're going to have to use the quotient rule again. So the derivative of the top is a negative sine times the bottom minus the top times the derivative of the bottom, which is just going to be cosine x, all over the denominator squared. And now let's clean it up. We will clean it up by distributing this through the parentheses and then just multiplying these things out. It looks like some nice things are just about to happen. Negative sine x, let's see, minus sine squared x. What happened with that? Negative sine squared x, and then minus a cosine squared x over 1 plus sine x squared. Ooh, look at this. Look at this business. This sine x squared and this cosine, all of these things have a negative in common. I'm going to pull out the negative just so you can see what happens. So negative sine x plus sine squared x plus cosine squared x all over, that same thing squared. Okay, I did that because remember your Pythagorean identity that sine squared x plus cosine squared x is equal to 1. So I'm going to plug that in there for this piece, and I get negative of sine x plus 1 over 1 plus sine x squared. What do you know? Look at this. This whole top cancels out with one of these factors to give me a negative 1 over 1 plus sine x. Man, that turned out to be really super nice. Here, let's add an extra page because we're not done and we need more space. All right, why did I do that? I found the first derivative so I can find some critical numbers. Critical numbers are, of course, where this is equal to 0, which doesn't happen because we have a constant number up top, and where it's undefined. Well, it's going to be undefined at the exact same places where you have vertical asymptotes, right? Because the denominators remained the same. The denominator was the same. So the only place where this is undefined is at our vertical asymptotes, which means there are no critical numbers. No critical numbers. If you have no critical numbers, this also means you have no relative min or max points. And inside each one of these little intervals, that means that it's going to have one type of either increasing or decreasing. And we can see from these little points here that our y values are going down as x's increase. So we know that it should be decreasing, but we're going to go ahead and do the calculus for it. So if we take a look at our first derivative here, and we have -1 over 1 plus sine x. Well, we know that the sine x is always a number in between a -1 and a +1. It can't be the -1 because we've taken that out of the domain. Can't be a little +1, which means that this number, if we're going to add 1 to it, this number down here is always going to be positive. And we're going to take -1 divided by a positive number, so this is always going to be less than 0 for all x in our interval from -π/2 to 3π/2. Since our first derivative is negative for all values of x in that interval, then that means that f of x must be decreasing, strictly monotonic, decreasing in each one of those intervals. So it means f of x is always decreasing in each one of these intervals. Okay, and let's see, we've done increasing and decreasing and relative extrema. Let's take the second derivative so that we can figure out concavity, possible points of inflection. So our first derivative, I'm going to rewrite this thing like this and totally avoid having to use the quotient rule on it. So -1 plus sine x to the -1 power, and take its second derivative thusly. So this -1 is going to leapfrog down and make it positive 1 plus sine x to the -2 power times the derivative of the interior, which is cosine. Rewrite this thing as try again. Cosine x over 1 plus sine x squared, which is super close to what the original function is. It's just that now the denominator is being squared down here. Okay, so we want to find our supercritical numbers. That's going to happen where this is either equal to 0 or undefined. I'm going to eliminate the undefined part of it just simply because the only place where this is going to be undefined is where the function is undefined. So get rid of them. We only want then where the top is equal to 0. So where is cosine x equal to 0? Well, I do believe we've already solved that earlier in this video, which took place about 3 or 4 hours ago, and that was at a π/2. It also happens at 3π/2, but you have to take that thing out of consideration. So this is a supercritical number. What can happen here? Well, okay, we got the web opening up there. On accident, what could happen here? We have a possible point of inflection. And if memory serves, those are our x-intercepts. So how do I tell if this is a point of inflection or not? I have to perform a test for concavity. Don't go thinking that this is the second derivative test, because it's not. What does the second derivative test for? Did you just say relative extrema? Because if you did, you're right. Intervals. And once again, we're just going to do one of these little intervals from -π/2 to our π/2. And then we have ourselves an asymptote right there. And then from π/2, we don't have an asymptote. We have an asymptote here. This is x-intercept. Come on. π/2 to 3π/2. And we need some x values, some test values here. And let's see, how about we choose something like 0 for this one? That should be easy. Oh, stop zooming out and in. It's annoying. All right, what should we choose for from π/2? How about pi? Yeah, that should make sense. Okay, so now whenever I look at my second derivative in this a final form right here, I could ignore the bottom because the bottom is always going to be a positive number. All I really care about is the top here, cosine x. It's going to completely determine the sign of this. Plug in this test value in the second derivative. If I plug in 0 up in here, cosine of 0 is 1, which is a positive number. So this is positive, meaning that f of x is a concave up kind of shape. And if I plug in pi, and for cosine you get a -1, the negative value, and then it's concave down, a CD. Concave up, concave down. We found ourselves a point of inflection. At, I think it was pi over 2 comma 0, since f double prime changes signs and x is equal to pi over 2. What is that garbage? Get rid of it. Okay, x is equal to pi over 2. All right, I think that we now have enough information to graph this thing, as if we couldn't have figured out what the graph looked like before. So in each one of these little intervals, it's always decreasing. And on the left side of this pi over 2, it's got to be not only decreasing, but concave up. This is a point of inflection. And then concave downwards from here. So it should look sort of like the cotangent function here. And then just duplicate that. Just make yourself an ink stamp and connect the dots. Man, that was glorious. Do you see how well I made that dot happen? Okay. And then this one is going to, no, try that again. So, right? And then maybe a couple more of these things. Okay, so I started shaking there. I'm getting super nervous. Oh, that was terrible. Here, let me try it from this side. Oh, that's even worse. Yeah, let's go with it. All right, that looks pretty good. Looks pretty sweet. Let's see what the PowerPoint says about all of this business. Come back over here and over here. And here are our x-intercepts, I guess. Here's our vertical asymptotes. And voila, each one of our little intervals. Yeah, that's approximately what we got there. All right, there you go. There's your lesson on curve sketching. It was a very nice way to kind of summarize the whole entire chapter, all the stuff that we've done so far about being able to put the pieces of calculus together to help us analyze and sketch the graph of a function.